Good afternoon, everyone, and welcome to another AABC Tab Talk webinar. My name is Sam Schwartz, and I'll be your moderator today. Before we get started, I'm going to cover just a few notes. We encourage you to submit questions at any time using the Q&A button, but we will be holding the Q&A session at the end of the presentation, but please don't hesitate to submit any questions as they come up. The chat function is open and where you can make general comments and chat with attendees. If you happen to be experiencing any technical issues at all during the webinar, please use that chat function to inform the panelists and we will assist you. And then finally, this course has been approved for 1 hour of continuing education credit. And after the webinar, everyone will receive an automated email with their proof of attendance. And please do wait at least 24 hours for that email to come through. And today's webinar, we're going to talk about hydronic system performance with David Glasgow and Cody Shook. David is a regional applications consultant for Belimo Air Controls. In the role of RAC, David assists consulting engineers and customers with applications and up-to-date technologies surrounding all Belimo products. He comes from a background in BAS controls, and that spans over 20 years, encompassing responsibilities as a field technician, applications engineer, programmer, project manager, and of course, as well as sales and business development. And he's joined by an AABC member that many of you probably are familiar with, Cody Shook. He's a licensed professional engineer, TBE and CXA with over 25 years of relevant experience. He is the president owner of Precision Flow Engineering. Founded in 2013, he and his firm quickly established themselves as a trusted tab and commissioning expert, specializing in healthcare, surgery, laboratory, and the pharmaceutical industry. So without taking up any more precious time today, I'm going to kick it off to David and Cody to kick us off and get into things.
Thank you very much. I appreciate the introduction, and I'm happy to be here today. I'm going to share my screen here and start off the presentation. Cody, do you have anything before I get started?
No, sir, Dave. It's all yours, man.
Okay. So everybody should see my screen. Maybe not.
I see it.
Okay. So today we're going to be talking about hydronic system performance. Why design and modeling data can't always predict a building's actual performance. Our learning objectives today are to explore the design and modeling assumptions regarding hydronic systems, identify the system performance issues that are caused by improperly sized control valves and poor valve authority, understand how variances in coil performance affects thermal heat transfer efficiency, discover how advanced control valves offer potential solutions for all of these issues. And we're going to jump right into design and modeling assumptions. So energy modeling software is limited in their capacity to model a truly dynamic system. As a result, there are 3 assumptions that are made regarding control valves that are not accurate in most hydronic installations today. We're going to go through those. The first one would be proper valve sizing. The second one is stable system pressures. And a third one is perfect valve authority. So we're going to start off this with a question to the group. And this is just a hypothetical question as what is a design day? Okay. Furthermore, traditional design processes are developed around this design day. A design day, of course, is the hottest day of the year, or the worst conditions that we have in the building to be able to overcome. Typically, they encompass only 3 to 5 days of the year and only about 3 to 4 hours of each of those days. So by that logic, the building is designed around a circumstance that is likely only to happen about 16 hours a year. What that equates to is 0.2% of the time of the year it's in a design condition. The rest of the time, everything is oversized. So let's start off with valve sizing. In order to understand that system level performance and the issues, we first need to understand some basics of heat transfer. What we have here is a coil curve. That flow rate increases as we go out the x-axis, and coil power increases as we go up the y-axis. Note that the coil curve is not linear. At that low flow rate, each molecule of water spends a long time in the coil, and it absorbs a proportionally large amount of heat. So small increases in flow make large increases in heat transfer. This is why that curve is steep at low flow, and at high flow rates, the curve rate starts to flatten. And this is because each molecule of water only spends a short amount of time in that coil. So many more are needed to increase that heat transfer rate. As you can imagine, this nonlinear shape is basically difficult to do any control with. So what we have is a control valve with an opposing shape. Here the axes are different. The x-axis is the valve opening or control signal, while the y-axis is the flow through the valve. The valve by design opens very slowly to counteract the fast-acting nature of a coil at low flows. Okay, so if you take a look at this, what it does is it gives you a linear output that results. And if you chart this, about 20 to 25% of the flow is about 50% of your heat transfer in that linear resulting output. The idea is that with a properly sized valve and coil, that linear result will occur when plotting the control command versus the coil output, essentially canceling each other out. And that's where that linear line comes from. So when we size pressure dependent valves, we use this formula. This is the flow coefficient formula that many of us are familiar with. This formula shows that flow will vary by the square root of the pressure drop. Okay, so GPM is typically the max GPM of the coil or heat exchanger. Pressure drop is figured in one of three ways. Flat specified, a fixed value from a design or consulting engineer. This is most common and typically is between 3 to 5 PSI, which is your ASHRAE standard. Selected based on the pressure drop of the coil or heat exchanger. The pressure drop would be greater than or equal to that of the coil, or pressure drop is determined by valve authority. Of these three ways, the first two are wrong most of the time. And the last one is impossible with the information given to the controls contractor that is selecting the valve or the contractor that is selecting the valve. At Belimo, we utilize 4, and that's what we're going to utilize for this example. The square root of 4 is 2. So your CV is essentially half of your GPM. So if we have a coil that requires 250 GPM with a 4-pound pressure drop, we have a CV of 125. What happens is that contractor will go to a catalog, and here is a page from the Belimo catalog, and you will see our first problem. We do not have a valve with a 125 CV, but we have 2 valves that we can choose from, one at 90 CV and one at 170 CV. So which one should we choose? Well, to determine that, we would have to solve for the pressure drop and reverse that math. So if we plug in the 90 CV, we get a result of 7.7 PSI, which is over that 4-pound pressure drop that is required. So we solve for the 170, which gives us a 2.2-pound pressure drop. This pressure drop would be acceptable, and we would choose that valve. A valve with 170 CV requires only 2.2 PSI to achieve that 250 GPM. What this means is that our already designed valve that is oversized is even more significantly oversized at this point. So we have our first poll question. And here it is here, but I believe there it is. If everybody could choose their answer, we'll give it a few moments. Okay. Pressure dependent control valves are sized for a design CV. I'm going to close that. And the correct answer was B. Pressure dependent control valves are sized for a design day, hottest day of the year. So here we're going to discuss three possible ways we could pipe the control valve that we selected with a coil. The first is a coil or a branch that has no balancing device. The second is going to be with a manual balancing valve. And the third one is going to be with an automatic balancing valve or an automatic circuit setter or flow limiting valve. So let's say we have a simple direct return piping system. In this configuration, we have higher pressure drops across the branches that are closest to the pump and lower pressure drops further away, as shown here. The far zone typically has low pressure drops and therefore it's very controllable. The fact that there's no balancing valve won't have much effect on this coil or this zone, and that's with no balance. So with no balancing valve, that closed zone is massively overpressurized and overflow is inevitable. The closed zone is highly unstable and essentially behaves like an on-off control valve. We have bad valve authority there. So if we redraw this model so that now we have the included manual balancing valves. In this configuration, the far zone is under control, as it was with the no balancing valve, and that close zone is balanced at full flow, but is unprotected from pressure fluctuations and will experience the effects of poor valve authority as flow decreases. So if we replace that and exchange that for a automatic flow valve or flow limiting valve, in this configuration, again, the far zone is still under control, and that close zone is balanced at full flow and protected from overflow at full flow. But it'll experience the effects of poor valve authority as flow decreases. So we've mentioned valve authority a few times now. So let's define it. The valve authority is simply how it relates to the branch schematic. Okay, it is the ratio of the differential pressure of the valve and the differential pressure of the branch. So if we look at this diagram here, the differential pressure across the valve is on the either side of that valve, and the differential pressure of the branch encompasses everything that is on that branch. So what if instead of just that one fan coil, we have a series of 4 connected by a direct return piping system? Here we see those 4 that are piped together, but since this is a direct return system, we know the far zone will have a relatively low pressure drop, and in this case, it's going to be 10. And each zone, as we get closer to the water source, will have an increasingly higher delta P. In this example, let's just look at the 2 extremes. The far zone at full flow at the branch, far from the pump, the coil will take its design pressure drop, in this case 4 psi, and the valve was sized for that 4-pound pressure drop. This leaves 2 psi for the balancing valve to consume. So we have a valve authority of 4/10 or 0.4 is 40%. As we said earlier, this VAR zone is typically under control. And here we see a favorable valve authority of 0.4. Perfect valve authority is 1. That is what we're shooting for. But because it's a ratio, we will never achieve a perfect 1. So we try to shoot for as close to 1 as we possibly can. That close zone at full flow, the branch near the pump, the coil will take its design pressure drop, 4. The valve was sized for a 4-pound pressure drop, and this leaves that balance valve to take up 12 pounds of pressure for that to equalize that branch. This is a valve authority of 4. Of course, 4 divided by 20 is 0.2 or 20%. This is an unfavorable valve authority, and it'll lead to control issues when the building is not in design or full flow conditions. Essentially, this will be acting as a 2-position or quick opening valve. So in order to understand potential troubles, we need to understand how balancing valves work, right? I'm sure many of you, or if not all of you, understand this already, but we'll go through it anyway. A manual balancing valve works if the valve is fully open, there's 100% flow balancing condition, there's no pressure drop or a very small one. The pipe represents an unrestricted flow area. Note the 100% flow, no pressure drop while the balance valve is fully open. To increase the pressure drop to balance the loop, the handles turn, causing the effective diameter of the opening to shrink. The opening of the pipe shrinks, representing a smaller area in which to pass the same amount of water. That's what creates your pressure loss. Moving the same amount of water through a smaller area requires energy in the form of pressure. So at 100% flow, which is a balancing condition, this smaller opening creates that 12 pounds of pressure drop that we're looking for, or pressure loss. So if at 100% flow, this smaller opening creates a 12-pound pressure loss, what happens at 20% flow? How much pressure loss is created if it's only at that 20%? Is that smaller opening large enough to accommodate 1/5 of the flow without creating a 12-pound pressure drop? Absolutely. So systems are balanced at a static condition, 100% flow, as we all know. And that means they're only truly in balance at that condition. All other conditions have potential for pressure balancing issues. But why did we choose 20% flow rate for this example? Isn't that a pretty low flow rate? Actually, it's not. Remember from our look at the coil curve earlier, 20% flow through a water coil will produce about 50% of the heat transfer, as shown here. This represents roughly a 50% control command to the valve. But how about a flow limiting valve? Well, what happens below max flow? Essentially, a flow limiting device only caps out the maximum flow. But let's look at an article from the ASHRAE Journal of February 2017. In this article, the author states, the flow limiting valve essentially does nothing when flow is below design. So the following 3 lines are also quite excellent to support this case. So let's go back to our building and turn those pumps down to 20%, command the valves to 50% open. What do the pressures look like now? So that FAR zone, 1 psi is now being seen across that balancing valve. So we have less than 4 pounds on the coil, but for the conversation's sake, we'll say that it's still 4. And that means that our control valve is now taking up that additional pound of pressure. It's a slight overpressurization on the control valve, but nothing that can't be overcome. We still have pretty good valve authority, and we have pretty good control of that zone. Now let's take a look at that close zone. So that balancing valve that was taking up 12 PSI is now seeing 2 pounds of pressure drop across it. We still have less than 4 pounds on that coil, but for conversation's sake, we'll say that it's 4. That means that we have a massive overflow on that valve of 10 pounds, and we have poor valve authority caused by that overflow. It makes it almost impossible to control that valve at low loads in these spaces. So let's move to poll question 2. If you guys can pull that up. At partial flows, which valves have an increased possibility of suffering bad valve authority? Valves furthest from the pumping source, valves in the middle of the hydronic system, valves closest to the pumping source. I'll give you a few moments to valves closest to the pumping source. So the correct answer was C, valves closest to the pumping source, correct. Let's look at coil performance now. So remember this graph from earlier, we discussed how the coil curve has a convex shape and starts to flatten out at high flow rates. But what we didn't add, and what we're going to add here now, is our delta T curve as well. You will notice that this has the opposite shape of the coil curve, but for the same reason. Those slow molecules of water that make the curve steep at low flows go into the coil very cool in a chill water application and come out lukewarm after being in the coil for a long time. This produces a high delta T. By the same logic, faster water will produce a lower delta T. So flow and delta T are inversely proportional. Let's look at this in a coil curve with a coil point cloud. The point cloud has a thickness, and that green line is simply just a best statistical fit of those points. The curve gets more shallow as the flow increases, and the BTUs at higher rates or flows are more expensive from a flow to load ratio perspective. So remember, this is our power output formula. But that power output formula also includes delta T. So if we show this delta T curve, in general, again, delta T decreases as the flow to load ratio decreases. What happens when the coil receives more than 100% of its design flow or its saturation point? Well, there are 3 penalties for overflowing. We're pumping more water, we're reducing the delta T's, and we're not producing any additional BTUs or minimal BTUs. So what we mean by not producing any additional BTUs is that the discharge air temperature and room temperature won't change at the same rate as before the overflow. And really with traditional control valves, there's no way to detect that overflow through measuring just the air temperatures. But if we look at this dot that is on this slide, that represents approximately 320,000 BTUs. If we draw a line straight across, you can see how that same load can be achieved at multiple flow rates by leveraging that thickness of the coil curve. Will we be able to do this at all times? No, but as this point cloud indicates, there are many times where we can have lower flows and still achieve that same BTU output. So if you look at this, because we talk about partial loads, we still have a thickness. It's likely due to normal variations in the heat transfer, but we can still achieve multiple or the same BTU output with multiple flows. So as a follow-up from the previous slide, most coil curves are going to have a much greater thickness. This would be indicative of a coil that's been in place for a little bit longer. That variation in flows, if you look here, that's a lot of BTU, 250,000 BTUs, and there were a lot of various flows that were used to achieve that. This here, although you don't see a traditional curve, there are pockets of dense data which represent delta T's. And what this shows us is that we can try to stay on the top side of that dotted line and achieve better delta T's with lower flows. So this right here is real life data collected from an energy valve installed at MIT. The diminishing return of BTUs as flow reached 55 GPM. But let's look at two potential operating points and their energy impact. So point one, we're achieving 320,000 BTUs at 55 GPM. Point two is 325,000 BTUs at 65 GPM. So if we look at that, there is less than 2% more BTUs. We're utilizing 18% more water. And if we put this into our pump affinity law, the horsepower requirements increase by the cube of the increase in flow. Between point one and point two, there is a 65% increase in pumping cost to achieve 1.6% increase in cooling. It's not very efficient. So moving on to poll question 3. What happens to delta T when flow increases through a coil? Delta T increases, delta T decreases, or delta T remains the same? Okay, majority of you said delta T decreases. So answer B, delta T decreases, correct. So remember, this is what we're modeling. So what can we put in a building to actually work like this? And again, we went through proper valve sizing. We went through perfect valve authority. And we went through stable system pressures. And we discussed how none of those are true in most applications. But we can look at a potential solution of pressure-independent control valves. And I apologize. So pressure-dependent systems are statically balanced. Pressure-independent systems are dynamically balanced. They're always balancing themselves. So as you know, we showed our fan coils. And we have different pressure drops or branch pressures as we move closer to that pumping source, it increases. But what you'll notice here is there are no balance devices. This would be a pressure independent system where that pressure independent valve is essentially giving exactly what that coil needs at all times and continually balancing with increases and decreases in pressures. So let's take a look at pressure independent valves. There are two ways to make valves pressure independent. This first is a mechanically regulated pressure independent valve. The valve is designed so that a variable amount of pressure is consumed by the regulator and that the control portion or ball always sees that same pressure going across it. So the flow goes right to left. P1 is your inlet pressure to the valve. P2 is the pressure after the loss going through the regulator. And P3 is the pressure after the loss going through the valve. Force from P3 pushes the regulator open. Force from P2 pushes the regulator closed. What that results in is that regulator continually moving back and forth, creating that constant pressure across the ball. So as the inlet pressure on P1 increases, so will P2, and then the force generated by P2 will cause the spring to compress and the regulator to squeeze more closed. The smaller area to push the water through will create a bigger pressure drop between P1 and P2, which will keep that pressure drop between P2 and P3 constant. Here's a pressure independent valve from another manufacturer. It looks quite different, but actually it works the same way. Flow goes left to right in this valve. The control valve portion goes up and down, it's a plug. And the regulator sits at the base of the product and actually works the opposite side of the same seat as the control valve. Pressure is sampled by the regulator from the outlet of the valve. So the needed pressure differential gets the needed pressure differential to activate the regulator. So although it looks quite different from the previous valve, we see that it gains pressure independence the same exact way. The second way is an energy or an EPIV, an electric pressure independent valve. It's actually a simple product to understand. It has the same design as a VAV, an airside VAV. Both use a flow measuring device, an air sensor on a VAV, and an electronic flow sensor on an EPIV, or an electronic pressure independent valve. This one is an ultrasonic flow meter with temperature and glycol compensation. It's chosen for its lack of moving parts and its low drift and maintenance requirements. Each one of those has a controller that accepts the flow measurement and logic that modulates the regulating device. And the valve actuator plays this role for an EPIV and interprets the control command as a specific GPM. The regulating device is represented by a damper on the VAV or a valve on the EPIV. The valve is driven by the actuator to achieve the proper flow rate. So poll question number 4, keep everyone on their toes. A mechanical pressure independent valve uses what device to achieve pressure independence? A flow meter, a regulator assembly, temperature sensors, or an advanced control algorithm? A regulator assembly, 84%. And the answer is correct, B, a regulator assembly. So moving on, a pressure-dependent system creates a situation where each zone is hydronically dependent on all the other zones. Again, pressure-dependent systems, meaning that a change in zone B may affect the flow rate and heat exchange in zone A and zone C. In this example, we have this building. It's been split into 3 thermal zones. Each zone is served by a small air handler, as you see here. Since we have a direct return piping system, we know that the pressure drop on each floor will be different. Suppose that the firm on the first floor only works till noon, and with no more load in the space, the valve would close. That means that the flow and pressure drop in that branch goes to 0. The extra pressure in the system is then distributed over to the other zones and they become overpressurized. The valves will overflow and cause too much heat transfer, and the discharge air temperature could be disrupted. Then the command will be sent to modulate the valve more closed, and all of this commotion happens with no changes in load to the space. And then, just in case that wasn't a big enough mess, the same time overpressurization of the far zone will cause the VFD to ramp down, which will then likely cause an underflow that'll need to be corrected. Eventually, the system will find a steady state, but it will see an anomaly in that time, or a mess. So now let's take that same building and pipe it with pressure independent valves. So we'll have the same pressure drops as before, but all of the zones are now hydronically isolated from one another. That same firm goes home at noon. The valve closes. Pressure drop and flow go to 0. Other zones overpressurize. But the pressure independent valves are unaffected by this overpressurization. The zone temperatures are stable and control to the system does not need to make any adjustments because the coil flow is unaffected. In fact, in a PI system or a pressure independent system, since all zones are hydronically isolated, the control system only needs to respond to changes in the load, not to every little change throughout the system. So another potential solution would be a smart valve with delta T management. That was supposed to be a video for you guys. But as you see here, there are 2 temperature sensors that are included. The low delta T is an indicator of inefficient heat transfer. Delta T manager will hold a delta T low limit threshold and force that coil to maintain that higher delta T while still achieving the load to the space, provided the delta T set point is properly installed. So let's suppose we had a delta T limit of 12 degrees, but the valve has overflowed and the delta T is now closer to 10 degrees. The coil is currently using about 63 GPM. The delta T manager detects a delta T lower than that threshold or that set point and will reduce the flow. As the flow decreases to about 55 GPM, the delta T rises to the set point of 12 degrees, and the power output stays relatively constant, taking advantage of that thickness of the coil curve point cloud as we discussed earlier. But let's note, we must pick a delta T set point appropriate for the coil. If we selected a 16-degree delta T on this coil, we would certainly starve that space. What we have here is a valve that was placed into 3 different control or limiting methods. Smart valves can be put into 3 modes, which are position control, which is a standard control valve operation, flow control, like an electronic pressure independent valve, or delta T management in that smart valve mode. So let's evaluate the performance of each of these at a given load of 60 tons. So at 60 tons, we utilize 240 GPM to achieve that 60 tons. In flow control, we utilized 144 GPM. And you'll notice that our delta T's increased from 6 to 10. When we put that valve into delta T management, we went to 96 GPM and we achieved the design of 15 degrees delta T to achieve that same 60-ton load. If you look at that, 96 GPM is a 60% reduction in the position control flow rate of 240 GPM to achieve that same load, which is a massive increase in efficiency. So the key takeaways from today are even the best designed buildings are oversized most of the year. Balance valves and automatic circuit setters are static devices only offering value at design conditions. And pressure independent valves create dynamically balanced systems and hydronically isolated loops. And last but not least, delta T management can optimize water usage during heat exchange. I want to thank everybody for their time today. I believe we have a few minutes for questions. I am going to leave this screen up here and I will pull up the Q&A if you guys the moderators want to read off some of those questions as they have come up.
Yes, absolutely. Thank you so much. And let's get into the Q&A session. If anyone has any additional questions, now is the time, hit that Q&A button and submit what you're thinking. So from one of our members, they asked, do the dynamic valves operate independently or are they, quote, managed by the BAS logic?
So pressure independent valves, that's a good question. Pressure independent valves are dynamically balanced, but they are still a control valve. They will take that 2 to 10 signal or 0 to 10 signal from the BAS just like a standard control valve, but instead of equating that to 0 to 100% open, it would be 0 to 100% of the rated flow for that coil. So take, for example, if you had a coil that had 100 GPM max flow for the design, 6 volts instead of being 50% open would be 50% or 50 GPM. That would essentially not necessarily be a valve position of 50%. Wherever that flow meter would see a 50 GPM reading is where that valve would stop. That could be at 40%, that could be at 60%. It could be anywhere that it achieves the GPM that it's required to have.
Great, thank you. And another couple just popped in. Someone is asking if you could talk about reverse return systems. Would they make a difference?
Reverse return systems might make a difference. Of course, you know, you're going to still have that pressure drop. So again, your pressure independent valves would definitely adjust for pressure fluctuations and flow fluctuations.
Next question. Are coil turbulators a good idea to maintain good heat transfer during low flow conditions?
Coil turbulators. I'm not 100% sure what you mean by a coil turbulator.
I think my follow-up question to that, Sam, would be, are they talking about the air side turbulators entering the coil, or is it some sort of water fitting? I'm not quite sure.
Okay, if Mr. Austin can submit a follow-up to that, then we'll return to that question.
Absolutely.
I'm familiar with an air side turbulator, not a water side.
Then a couple more questions keep coming in. So if PICV that have different differential ports. If minimum DP is 3 psi, can you calculate flow if only measuring 2.0 psi?
So if you're talking about a differential port, that's typically a manual balance, or not a manual, a mechanical pressure independent valve. The ports that are on our manual or our mechanical pressure independent valves are just there to determine whether we have the proper differential pressure for operation. In our case, it's 5 to 50 pounds of differential pressure that is required, and that is reliant on the spring that we use for that regulator.
So go ahead, Dave. I apologize.
Nope, go ahead.
No, I was going to say we've tested this in the field, but I would imagine that the straight answer to that question is it probably varies a little bit on the device and the manufacturer. We
Correct.
have seen it where, let's say, just that's typical 5 to 60 or 2 to 32 psi. If you're below the minimum psi, they actually will behave somewhat linearly below that psi, but only up to a point. And I can only speculate here, but I would imagine that varies quite a bit from manufacturer and device.
It does. They all have different spring rates. So if we say, or if a manufacturer says that the minimum DP across that pressure independent control valve is 3 psi, on a mechanical pressure independent valve, anything below the rated differential pressure, that ball valve will, or that valve will act as a pressure dependent valve because that spring is going to be static and it's not going to be taking up any of that pressure. So it would be a standard ball valve at that point. When you get into electronic pressure independent valves, they have a much lower differential pressure that is required. On ours, it is 1 pound of pressure drop that is possible and still be able to calculate that flow. But yes, you would definitely, if it goes below that, you're going to offset a little bit. Hope that answered your question.
And I do have a follow-up from that previous comment about the turbulators. They said that the turbulators are inside water tubes to maintain turbulent flow and heat transfer during low velocity inside the tubes. Pressure independent valves throttle flow well, but when the water flow becomes laminar, the heat transfer falls off dramatically.
Yes, I would agree that laminar flow is not beneficial to a system. I understand what you're saying. What the pressure independent valves do is they take up and they modulate to the changing flows and pressures that are in the system. I'm not familiar with sort of turbulators inside of the water tubes for that turbulent flow.
Okay, we could switch to another question.
I can definitely follow up on that question for you.
Okay, great. Is there a minimum spacing between balancing valves and control valves? I've been told that water can, quote, shoot through a balancing valve if the control valve is mounted too close.
Are you talking?
I can weigh in a little bit here. I don't know about shooting through. I've definitely seen that on air side, and that may very well be the case. But if we're just talking about old school circuit balancing valves mounted too close to control valve, we see that all the time. And I don't know about shooting through, but it absolutely can wreak havoc with getting back to laminar flow versus turbulent flow and coming up with any type of reliable differential. If you have, say, a control valve butted up against the balancing valve butted up against another fitting, which frankly is common in the field all the time. So yeah, that's a legitimate concern. Which I guess would bring a follow-up to Dave, is if maybe he can educate us on minimum spacing on some of these smarter devices with like not just delta T, but certainly with flow devices in them. Flow measuring devices, rather. So
on the electronic pressure independent valves and the energy valves, if you take a look at the way that they're designed, they have a flow meter that comes in and then, or on the incoming side, and then you have a following ball valve that is right after it. Because that ball valve is in that design, it eliminates any exiting pipe length requirements. But ours require 5 pipe length straight pipe runs. So if it is a 1-inch valve, you would need 5 inches of uninterrupted straight lengths to be able to install that valve and have correct flows.
Thank you. So there are even more some questions coming in. So keep them going, guys, if you have more. This next question is asking if there's a reduction of flows when you don't get to the minimum PSI for the PI valves, or excuse me, is there reduction of flows when you don't get to the minimum PSI for the PI valves?
Is there a reduction of flows when you don't get to the minimum PSI for the pressure independent valves? So again, mechanical, if you don't get the minimum differential pressure across that valve, it's going to act as a standard position valve, a standard control valve, because you're not going to have any fluctuation in that regulator to be able to get that. Most systems that you run into, you're going to have a minimum PSI, pressure drop across. Again, electronic, you can get down to that lower 1 pound of pressure drop. I don't know that I've seen less than 1 pound of pressure drop in an operating system that's correct. That 50 pounds of pressure, not many hydronic systems out there in the commercial space are going to be above 50 pounds of differential.
Should control valves be located upstream or downstream of the coils, and does it matter?
So we recommend all of the valves being put on the return side of the coil. Our smart valves, our EPIVs, and our energy valves, because of the nature of them, we have the ability to select whether it is in the upstream or supply side or not. And the reason for that is the delta T. So we recommend return side, but they can be put in the supply side if needed.
I'll just keep it going here. How would a PI-CV system compare cost-wise to a standard control valve with auto flow balance valves?
So of course, their pressure independent valves come with an increased cost. What we like to look at is overall cost. So with a pressure independent control valve, balancing is reduced because instead of doing manual balancing, you're doing flow verification, which still takes some time, but a little bit less than doing a manual balance through the system. You also have the reduced cost of not having to provide or install those balance devices. So there is a cost savings and an offset there, which brings it relatively close. But there is an upfront hardware cost increase between a standard ball valve or control valve and a pressure independent.
How do you field calibrate the electronic PI-CV? Can water flow be measured on the same water circuit to calibrate the ultrasonic flow meter?
So the way that Belimo utilizes or implements their ultrasonic flow meter is that at the factory, those are each put on a test bench and they are wet calibrated. The intent of that is so that they are calibrated for the lifetime of the product. We have not had any that have come back that are super out of calibration or have noticed any issues there so far. Of course, regular maintenance of the valve and the hydronic system is recommended.
Okay, we have time for just a few more questions. So if anyone else has any more questions, feel free to pop them in there. This next question is, does your data assume a constant flow system? How would the performance numbers change with pumps that are controlled based on a system DP?
So data, again, so a pressure independent valve is going to give the proper flow required. So if you're Pumps are controlled on a DP with a VFD, a variable frequency drive. The valves are going to stroke open based on that control signal. That control signal sends it a target GPM that it is looking for, and that valve looks at the flow meter data to be able to know when it has achieved that. So if you had a system and your VFD ramps down, of course, that flow meter is going to see less flow, which would then send that signal to the actuator to open that valve more to achieve that target flow. So they can be utilized in constant flow or, or a VFD based system.
Okay, and probably maybe the last question, if we have chance for one more, then I'll grab that. What tab requirements are there at each coil for a PICV system?
So in our documentation, we recommend mechanical contractors or installing contractors to put 3 PT ports, one across each side of the valve and one across the coil. And that allows for third-party verification of those flows. So instead of with a traditional balance device, putting those valves or the pumps at 100% and the valves 100% open, simulating that design day, and then taking your readings and adjusting that manual balancing valve, it's done statically or dynamically, and you can verify through those 3 ports that are installed and verify your readings and the the smart valves or the EPIVs are reading the same. So it transfers from a balancing to a verification.
Perfect. Thank you, Dave. One last question, and then we're going to wrap things up. What is causing the thickness you describe on your power versus flow charts? Is it the wide variance of building load?
So a lot of different variables go into that thickness. It could be, your load within the spaces. It could be outside air conditions. It could be operation of other valves in the system that cause that thickness. Again, we try to leverage that thickness in being able to control at a lower flow rate. And as I said, you're not maybe going to, in every instance, be able to hit that same flow to be able to get the BTUs, but a majority of the time, you should be able to leverage that thickness, which is controlled by a lot of different variables within that system.
Thank you so much. Unfortunately, that's all the time we have for questions, but thank you to our attendees who submitted all of those. Those were great. Dave and Cody, thank you so much for coming on and sharing your expertise today with AABC.
Thank you, everybody, for your time.
So as a quick outro, I just wanted to do a shout out to Tab Journal. Many of you have been reading for many years, but in case you're not in the know, we have approved them all for continuing education credits. So it's easy as reading an issue, going online, taking an easy 10-question quiz and passing. You can take it as many times as you need to, and you get a certificate of attendance emailed to you. And we just released our tab commissioning and energy management double issue, which we'll be doing annually now with the AABC Commissioning Group and the Energy Management Association. So it includes case studies on commissioning and energy management in addition to tab. So please do take a moment out of your day and head to that link down below to check them out. Thank you so much, and see you next time for the next AABC Tab Talk webinar.